The second speaker of the day is Dr. Ramneet Kaur. She is the alumna of Jammu University. She has completed her PhD in organic chemistry from University of Jammu, and presently she is working as a laboratory manager, Global Resource Recovery, Melbourne, Australia. Welcome, Ramneet ma'am. I have a request to you. Before starting your presentation, please let us tell us something about this global resource recovery. How does the company work, and what is their actual purpose there?
Sure. Let me share my screen first.
Yeah, please.
Very good morning to everyone. I am Dr. Ramneet Kaur, a laboratory manager, assistant operations manager in Global Resource Recovery. It is a waste industry in Melbourne, Australia. Here, I'm going to share a few slides to show you my company as well. Can you guys see it? Hello?
Yes, ma'am.
Oh, sure. Able to. Oh, yeah. Yeah. Yes. First of all, I would like to thank the organizing committee for giving me this opportunity. I did my PhD from University of Jammu, so it's been a real honor to be here. I'm a bit nervous as I'm in front of my peers and my colleagues, but it is really exciting opportunity to be part of it and to get it into the moment. Before I begin, I will tell you a bit about my background. I did my PhD in organic chemistry from University of Jammu with Professor Kamal K. Kapoor. University of Jammu. Then I went to Australia. I got opportunity to work in a waste industry. It was not where I want to go, but I end up into the waste environment. Since then, I'm running a laboratory. This is our laboratory. We do lab testing. We do compliance testing against our licenses. We do a lot of research and discussions, which is trying to develop the solutions for the problem. Our philosophy is about taking the waste and try to produce it into a commodity product. We develop lot of stimulations in our lab. We call them as a recipe. And in terms of making recipes to treat wastewater, to treat the high risk chemicals, we do the neutralization of concentrated acids, concentrated caustics, and we also treat oxidizers. We do a lot of CAs as well, like certificate of analysis. By the CAs mean like we take the waste glycol and oil from the market, and then we recycle into 99% glycol and oil and sell it to the market back. So our customers are even in Australia as well as in India, China, and overseas, other countries as well. So this is about my background, but today, the topic we are all here is to learn about the most recent advances in chemical sciences. I would like to tell you how waste industry has advanced in few years. A lot of advancement has been done in the field of waste industry, so we can process waste and make it into a product which is reusable and free of major pollutants. In my opinion, the advancement has been done in finding the contaminants, and then advancement is done in removing those contaminants rather than general advancement in science. In this slide, I want to show you, I have made this slide to just put a light on. Here is today we are having the advancement in science and advancement in equipments. With the help of these equipments, we are able to detect more contaminants. So when the contaminants are being detected, the scientific people can work on those contaminants. Once the contaminants are found, the EPA, Environmental Protective Authorities, and the regulators. They understand what sort of impurities are in the waste. So either they are organic, inorganic, physical, physiological impurities. Once these impurities are found, then the advancement is done, like the regulators put forward the limits on the discharge limit of the recycled product. Once once the limit has been put forward, it is the job of this laboratories basically to come forward and treat those impurities and find out, to do the research, to do analysis, to find out how we can treat this new advanced contaminant. Once this contaminant is found out, then we do the costing and we try to put forward the pilot reaction in the industries. Usually what happens, the research, the industry people try to mimic what is already done by these scientists. So sometimes what happens, whatever is done in the lab is not what we get outside. So to do that, to do this, like to get that stuff to be done in the processing, we do a lot of advancement, like we put the different instrument like engineering control as well to get those processing to be done. So research is applied in industries on large scale, and then again, when the research is applied, we get the recycled product. Again, the advancement of the equipment is used to detect the new chemical, and EPA government check the recycled product. If they are happy with it, they will ask you to discharge in the environment. So this is how the advancement in the waste industry has come up. So it's a cycle process. It goes from equipments to scientists to EPA, then to lab, industry, and again it goes the same round and round. So lab is basically the heart of every business, and our motto is to provide sustainable solution in the treatment of water and recycling water consistently. So since I told you we deal with different types of waste, but here I am planning to tell you about how the waste water is recycled in industry and what are the recent advances. Many people take water supply as granted. Only 1% of fresh water is useful for human consumption. Wastewater is waste. Wastewater is the waste which has been wastewater is the water which has been contaminated by humans and the nature, and it can be restored. And it can be restored by using various treatments. There are 3 different types of treatments: primary treatment, secondary treatment, and tertiary treatment. More you do the treatment, more costly will be the cost to produce the quality of the water. There are 3 different types of, as I told you, there are 3 different types of treatments: primary treatment, secondary, and tertiary. And every industrial plant can work either with one, or they can work in combo. Below is the below is the diagram, which I'm showing here is with the global resource recovery. Here is the truck. The truck came into our site, we accept it, and then we put the basket here to remove the grit out of it. Grit means the sand or the soil. We remove that by putting the basket in it, and then it goes to the tanks, where these are our tanks. We have like 4 storage capacity tanks, and each tank is 500,000 liter of capacity. And then the water come in here, and then we leave it there for a few days. It got sedimentation, and then if there is any soil or any kind of impurity, it will get settled down, and we will get the colloidal nature of the water floating at the top. So this is the primary treatment which we do. In our plant, we don't do the secondary treatment. Secondary treatment like activated sludge method, trickling filters, and the anaerobic digestions, they are basically the biological processes. We don't deal with them. We go straight to the tertiary treatment. Here we do from these storage tank, we take water straight into the treatment tanks, where we do the chemical coagulations and flocculations. We do oxidations, we do adsorption, and then once on treatment, a sludge is produced. This sludge is passed through the filter press. Usually we have the filter papers in lab, but in industry level, these are the filter presses. So the water is then the treated water, the sludge remain in these filter presses, remain in the membrane, and then treated water is then get back into our discharge tanks. This is how we treat the wastewater. So now, after treating the wastewater, so we fill the tanks. We have, as I told you, we got 2 discharge tanks. So one each of 500,000 capacity. Once it is treated, so our regulator, they have defined the toxic organic and inorganic chemicals. Before discharging that water into the sewer, we have to get that tested. And we have the specific limits to discharge. So there are different types of waste contaminant in wastewater. One is organic contaminants, inorganic contaminants, physical contaminant, and physiological contaminants. The major, some of the well-known primary contaminants are like PFAS, pesticides, oil, volatile organic compounds like benzene and toluene. In terms of inorganic, we got metals in their salts, ammonia in leachates, inorganic fertilizers, sulfides. In physical contamination, it is color, temperature, turbidity, and in physiological contamination is taste and odor. So as I told you, like regulators have has defined toxic organic and inorganic chemicals, and they put forward the specific limit. So here is the batch report, which I have attached here. So this is the essential list, which our regulators have given us. It has 58 primary pollutants. So the one which are essentially we need to test before discharging the liquid into the sewer. These are that. They are the 15. I can like highlight it so you can see there are different types of metals: chloroform scan, PFAS scan, benzenes, different types of benzene scans, alcohol scans, aromatic scans, and other ungrouped scans. So they are in total of 58 different items which we tested. If they, even on the sheet, they have given us the limit. If you look for the metals, if you look for the zinc here, zinc has a limit of 10 milligram per liter. So before discharge, if we have to meet these limits, if the limits are not met, then we are not allowed to discharge. This means the water will stay into the tank. We have to retreat whole 500,000 liter capacity of worth of tank. So in next first slide, I want to show you how, when I begin in global resource recovery as a laboratory assistant. So when I started, there was, we used to treat primary pollutants, but the amount of testing we do was only 12. So here is the list of the essentials which I'm sharing with you at the moment. It's 2018 and 19. So back those days, the regulators have given us just only 12, essentials which we have to do, and that's in 2018 in March. So as the time passes, the advancement has been done in the sciences. The regulator come to know about the more contaminated the contamination, they start giving us more list, they start adding the list on. And now that's in 2018, this is 2019. And then we got 2020, and we have testing primary pollutant as 49 we were testing. And then in 2021, we were testing 58 primary pollutants. And the same is still there in 2022. So out of various contaminants, I would like to put some light on one of the fast emerging contaminant in environment, and that is PFAS. PFAS, it is a group of manufactured chemical. Human beings have manufactured it, identified by signature chain of elemental bond between carbon and fluorine. This bond is so strong, that's why this molecule is hard to disintegrate in the nature. PFAS is used in a variety of industries because of its ability to repel oil and water. PFAS is known as perfluoroalkyl substances and also polyfluoroalkyl substances. By perfluoroalkyl substances, it means all the carbon atoms are attached, except the one, all the carbon atoms are attached to fluorine, except the one which is attached to the functional group. And for polyfluoroalkyl substances, at least one of the carbon is attached to the fluorine. So there are almost 4,000 different types of PFAS widely studied, but the 3 of them are, only 4,000 have been identified, but the widely studied PFAS are only three. That is PFOS, PFOA, and PFHSX. So these PFAS molecules, they are found in our household, in our non-stick pans, the carpets, water repellent, cleaning products, in our shampoos. These are found in firefighting foam. These are found in those areas where the firefighting foam area, where they, in the firefighting stations, it is the maximum quantity that is found there. And then we find it in our pizza boxes, in microwave popcorn bags, and in our dental floss, even in our cosmetics, in our food. Sometimes we find it in there, and in also when you treat the PFAS contaminated water into the wastewater treatment plant, the sludge which is obtained, if you, without letting know the EPA, without testing it, if you simply put it into the landfill, that if it is converted into the fertilizer, that is the biosolid, which is also the contaminated. So worldwide major concern for PFAS has been put forward because they stay in environment for so long that scientists are unable to estimate its half-life. That is the amount of time it takes for 50% of the chemical to disappear. They move easily from animals to water and the land, and they build up in animal and in people via food, like they stay in human kidney, liver, and in lungs. So the Environmental Protective Authority, that is EPA, has taken some precautionary steps to regulate the disposal, its management, and reuse of PFAS. Further, they are also putting forward the regulatory limit to discharge into the sewer. If any of the company is receiving PFAS contaminated water, when they do the treatment, when they fill their tanks, discharge tanks, before the discharge, they have to go through their for the external testing, and that external testing should have the results 0.001 milligram per liter. That's the limit. So that is 1 ppb. So here we in this diagram which I put, that's one of my favorite, because this diagram shows you like PFAS. Here is the contaminated landfill, like all the soil sludge which is contaminated PFAS is here. This is the firefighting foam, the military bases, the airports, and some of the sources, like even if you have the there where they have the firefighting training, those areas, and the manufacturing PFAS and the wastewater contaminating PFAS site. They all have, if it is not regulated, then everything will go into this river, and slowly it will go to our drinking water. So PFAS will be found soon in our drinking water. So now I want to show you how how in global resource recovery, because this PFAS was not in our essential list till 2021. So we got this PFAS, and we were getting it. Our limit was 1 ppb in each of them, like PFOS, PFOA, and PFHX. So, but the sample we are getting was much higher. So we were getting like 5.4 ppb, but our limit was 1 ppb. So we tried to treat it, like how we can treat it, through our wastewater treatment plant, and then this can be treated, and we protect the environment at the end. That was our main motto. Like, we don't want to discharge anything in the environment which is high in PFAS values, and then ultimately which risk the environment here. So first of all, what we did the treatment of PFAS water with our normal technique. What we did, so this was the untreated water which is coming straight from the tanks, and then so the wastewater has a colloidal particle which are negatively charged, so they repel each other. So two colloidal particles which are negatively charged, so they are so we add ferric chloride, which is acidic coagulant. We add it, and the coagulant absorb onto the impurities. It reduces the repulsive nature, and we start getting the precipitation. But the precipitation with the acidic coagulant is really very light. So we cannot filter it through with normal filter paper. It's very light. So, and also the pH of the solution is very low. The precipitation, although you can get a sludge, but the pH is 2.5, which is acidic, which is not helpful, which is not good for our environment as well. So we treat it with, to bring the pH high, we add another coagulant, that is lime, and lime help in adjustment of pH and neutralization of the sludge, which help in the precipitation of various metals, also at the pH of 9.5 to 11. And then we add the flocculant polymer, and then the separation of solid particle from liquid, and a loose aggregation or soft flakes are formed. Those soft flakes, they settle at the bottom, and we take out this liquid, and this liquid will go straight into our discharge tank. So when we found this liquid, we get it tested, and then we found, like, the untreated one is here. So untreated is here. We got PFOS is 5.4 ppb, PFOA 0.314, and PFAX 0.83. A fact you can see, P4 and PFH, they are compliant, like they are below 1 ppb, but PFOS is 5.4. As I told you, our limit is 1 ppb. So after this post-treatment, we find it out as PFOS as 4.1 ppb. Since we are not compliant even, so the regulators, they will not allow us to discharge. We will leave the tank as it. Either we have few options, either we just retreat whole tank, or we stop our production. So these are the few. This is the to avoid these things, we started researching regarding how we can treat this PFAS. So we found a lot of work has been done around activated carbon. So the activated carbon absorb the natural and synthetic organic compounds. So they are highly porous material and provide large space area to which contaminant can absorb. We found that the granular activated carbon is highly effective than the powder form. And the granular activated carbon, it work well in PFOS and PFOA. There is a lot of research papers which have been proved. But on the research papers, they were saying, like, if you only 95 if you pass PFAS water from activated carbon itself, it will give you 95% of 95% of elimination. But when we tried in our plant, it was not that effective for us. So activated carbon, then we tried different other sources, which I'm going to tell you in the next slide. So how the mechanism of the activated carbon works, the absorption of PFAS compound by the carbon media. There are two types of interaction. One is the electrostatic, another one is hydrophobic. The electrostatic interaction, it occurs between the anionic functional group of PFAS and the positive site of the adsorbent. While the hydrophobic is between the the hydrophobic tail of the PFAS with the hydrophobic surface of the adsorbent. So what we did, when we pass the wastewater through the carbon system, like just from the carbon system, we actually created one in the lab, and we just put our liquid straight from the carbon into the carbon system. We found like the initial data, 5.4 ppb is same as 5.4 ppb. There was no change in that. We haven't noticed any change. And but the thing was we do see the reduce in our metals, in the color was becoming clear, and other properties have gone off, but not the not the PFAS. So we would be think of from here, before doing the carbon system, we try to treat it with the wastewater treatment plant first. So we did on the sample, on the actual sample, we flock it, and then we pass it through the carbon system. So the activated carbon system are the two proper tanks. So first it goes from the inlet here, and then some of the PFAS is most of the PFAS, is adsorbed, and then it goes into the second chamber where most of the rest, whatever is left, is also adsorbed. So in this table, you can see that the pre-treatment, like the actual sample was 5.4, as I told you. The post-treatment with wastewater treatment plant is 4.1 ppb, but after passing it through same liquid through the carbon, we got 3.3 ppb of PFOS. So you can see there is the change in the the numbers are decreasing, but still our limit was 1 ppb. We are still not satisfied with this. So in the next, we did the optimization of the reaction. We found, like in wastewater treatment plant, when we were treating here, we were using ferric chloride as our acidic coagulant. So this ferric chloride, we were using just 1.5%, which means in 100 ml of sample, we were using 1.5 ml of ferric chloride. And for bigger batches, like 10,000 liter of water, we will be using 150 liter of ferric chloride. And the PFOS was coming down to 4.1 ppb from 5.4 ppb. So the idea from here, we thought, why not we just increase the amount of ferric, like acid. Let's just increase the amount of acid. So we started increasing from 1.5 to 3% ferric, and then we did 5% ferric. With 3% ferric, we noticed, like in 10,000 liter of batch, if we add 300 liters of ferric, the PFOS has gone to 3.6 ppb, and in 5% ferric, it's gone to 2.9 ppb. So we cannot go more than 5% because it's not appropriate to go beyond 5% as per our operational needs. So we just stick ourselves to 5% ferric, and then we concluded like PFOS removal has enhanced at lower temperatures because these reactions are done in the normal room temperatures and on addition of more ferric coagulant. So when we see the ferric coagulant, it has been reduced to 2.9 ppb. So again, we thought, this acid we are using here is just 5%. Why not we just treat PFAS in neutralization of acids? Like, why not we just use this PFAS water as a water of neutralization? So in the next slide, because we haven't yet met our target, it is still 2.9 ppb. So in the next slide, I will show you what we thought then in the next step. Like as we were using acid here, in percentages, we want to use this PFAS directly in the neutralization process. How? I'm going to show you. So in a lab, what we do, as I told you, we also treat strong acids and caustics. So in industry, whenever, as in a rule of thumb as well, we always add water first and then we add acid. So we add water and then we add strong HCl and then we add caustic on it. We get salt plus water. That's the basic neutralization reaction. So this is what the similar we apply in our neutralization reactor. So this is the diagram which represents a neutralizer reactor. So we have the acid line pipes coming in, we have caustic pipes coming in, we have mixer, we have pH controller, we have level sensor. So now the only thing is to change it. Instead of adding water first, what we did, we usually add the normal water. Here we added 5,000 liters of water in it. So we were about to treat 5,000 liters of acid. So we added the equal amount of water, which we earlier adding. It's just water, we adding PFAS waters. So when we added PFAS water in here, and then we treated normally like normal neutralization batch, we added acid and then we added caustic, we treated it. This was the neutralization we did. After that, this neutralization, the product which is obtained, we send it to the wastewater treatment plant, because when you do neutralization, a sludge is contained, that sludge is treated in wastewater treatment plant. So from this neutralization, we go ahead and we did testing. Similar Viva sample we had, it was having 5.4 ppb of the testing of PFOS. But here with neutralization step, we noticed the PFOS has dropped to 2.2 ppb in our case here, which was a dramatic change from going through straight from wastewater treatment plant. We were achieving only we were receiving 4.1 in initial and then using 5%, 2.9, but in neutralizer, we were getting 2.2 ppb. So then the next step, we thought we just send it to wastewater treatment plant, use 5% ferric, and then treat it normally, send it through the filter presses, and then that filtered water That filter water we again tested. Once we treated it with 5% ferric, we got 1.5 pp, 1.5 ppb. But still, we haven't met our target. Our target was 1 or less than 1 ppb. So the next step we did, we passed it through carbon system, granule activated carbon. After passing it here, all the water has been collected in the trade waste. We sampled the trade waste and we found the neutralization reaction with wastewater treatment plant plus activated carbon is we got 0.78 ppb. So we achieved our target, just not just by using activated carbon, not just by using wastewater treatment plant. We did receive our target by achieving it by using neutralization, wastewater treatment plant, and then using the activated carbon. So now our ppb limit is less than 1 ppb of PFOS, P4, and PFHS. Once this is achieved, our next step is we do the operational cost behind it. Like if we treat this much of water, it's going through neutralization, wastewater treatment plant, and activated carbon, how much price it will be monthly or how much it would be the costly. After doing it, we found it is operationally fit for us, and we are processing minimum 10,000 liters of, 10,000 kilos of waste of PFAS throughout the plant every day. We do have operational challenges because after every 400,000 kilos of processing, carbon becomes spent. So every fortnight we have to change the carbon, and we have to take out that carbon, and we by using our sludge management, we solidify it. It's already solidified. We mix it with the other solidifying agents, and then we give it into the landfills. So in conclusion, only one, in present work described, only one process is not effective to achieve the success in industry level. So we need to combine different processes. So we achieve the target of less than 1 ppb of PFOS, P4, and PFHS-X. This process is active in plant since 2021 and will be sustainable. So what are the noteworthy advantages we noticed? Like we used our plant own capability without bringing much change in the processing waste through the wastewater treatment plant or neutralization. By that I mean we never change any chemical, we never change any other processing. We were doing the same thing, just the changes, just the change in thought process and using the research, and then using the advanced technique of the contamination founding, like the advanced instruments. So we figured out with the help of those, and then we also installed the carbon system, which is part of it. And then PFAS has gone less than 1 ppb. Production is running smooth. We are on one of the leading companies in treating PFAS in Victoria, Melbourne. So now our next target, this is the target was for 2021. Now our next target is, as we clean the carbon system, we read a paper, like as I'm telling you, we are doing, these are the advances in the chemical sciences. Like the researchers, they do their task in the lab, and we in the industry, we try to implement in our industry as industrial chemists. So now we are cleaning up of the carbon system, which with HCl, we found like when we change our carbon every fortnight, so they clean it with HCl, which it's the thought process behind that cleaning is to increase the density of positive charge, therefore increases the electrostatic attraction of negatively charged PFAS molecules. So now what we are looking at this year target is to see how much of HCl is required to clean the carbon system. And if we use more of HCl, will it increase the more positive charge in the carbon system, and which ultimately, instead of changing it into fortnightly, can we change it like in 3 weeks times or 4 weeks in months time, or maybe it increase our production, like instead of treating 400,000 liter of water as a processed clean water, maybe it will treat 500,000. So this is our target for in next few months. Probably we will come up with the new strategy. So this is all from my end. Thank you for your patience. This is our lab team, which we all work together. The first is myself, Ramneet, and then Nick Amy, V, and Ron. We all work together, and we do a lot of research and discussions. We bring out, few of them are like, they are chemical engineers. Some are like myself and Mick, we are like from the chemistry background. So which is interesting, great. And we are helping environment, we are helping the community, which is great. So I would like to thank the organizing committee for giving me this opportunity. If anybody has any question, please you can.
Any
Hello.
questions from the participants?
Ramneet, can you switch on your video?
Yes, sir. Sorry, it was not.
Oh, happy to see you.
Oh,
Great to
thank you,
see.
sir. Thank you, sir.
So, first of all, I congratulate you for
Oh,
your target-oriented work, and
thank you, sir.
especially I could see the results about the PFAS treatment
Yes,
is
sir.
very encouraging.
Yes,
It's
sir.
very encouraging. I don't know how much time you are taking in the retention during the treatment of that PFAS.
Yes, sir. So usually we just do it instantly. It happens in a day. We do a batch sheet, and with the full process, it usually take 6 to 7 hours with full like neutralization, wastewater treatment plant, then going through the carbon. But in the carbon system, for every
No, that
yes, sir.
acid-base neutralization.
Yes, sir.
Yeah. How much retention time is there in the tank?
It's we don't like 15 minutes just when the caustic solution, we just want to achieve the caustic pH to 9. That's it.
But I think you should increase little bit retention time.
So it will help
Yeah,
further.
I
So
hope. Yeah,
okay.
yeah,
So I will try that. We will try
yeah.
that definitely. Yeah.
Just. But happy to see you in the lab base and
Yes.
feeling proud.
Thank you, sir.
Great.
Thank you,
All the
sir.
best. Right.
Any other question from the participants? I think there is no question. Ramneet, thank you very much. Thank you very much for sharing your practical experience with the lab. And we are very thankful to you that you spared your time because of your tight meeting schedules. And you told me that COVID is at peak in Australia. And we are also
Yeah.
facing the same situations, even the presenters that we have today for abstracts. Some of them are reported to be COVID positive and may not be able to speak. But we cannot avoid this, what we can see about the time we are facing. Still, we are very thankful to you that you spared your time. Hopefully next time when you will be asked to present, you would share your expertise with us.
Yeah, sure. It was my pleasure because I'm in front of my peers, my professors, so and my colleagues. So it's real immense pleasure for myself. So I would like I would be very happy if Professor Kapoor would be here. I want to give him an invitation in first place, and then I thought, oh, I don't know how I'm gonna express my views over there because he has actually trained me. He came to Australia. He saw my plant. He know what I'm doing here now. So, but obviously this is a recorded session. I'm definitely going to give to sir like I did it. And that's my first time. I'm hopeful I am able to give my best, like everybody understood what we are doing. And I want to make it a very easy for the graduates as well, so they can understand, like, it's not the very fancy chemistry, but it's definitely a simple chemistry we can do when we can make a definite difference in the community.
Thank you, Ramneet. Thank you very much. Thank you very much.
Thank you.
So now we have with us the sir. Sorry, I could not welcome you earlier because of the session you joined in between. I welcome Professor Sushil Kumar Pandey. He is the professor of Inorganic Chemistry, University of Jammu, and our revered teacher. I think everyone who has joined the meeting from any part of JNK have been the student of Pandey sir. And sir, we appreciate you very much. His field of specialization include diethyl-phosphate chemistry, sulfur nitrogen, phosphorus nitrogen chemistry, alkoxide chemistry, and fluorine chemistry. He has, to his credit, many visiting scientist fellowship and Humboldt fellowship. He has many research papers of national and international repute to his credit, and he has held many academic and administrative positions at the University of Jammu. Sir, we are privileged to have you with us, especially with our undergraduate students that are studying in Parade College.
Thank
Many
you.
times we have told your examples that you used to put in the lab before our students, and they might feel motivated and encouraged to see you here. Welcome you, sir.
Thank you.
Sir
Gurpreet ma'am, I want to say something about
please.
Pandey sir. Like we used to do in our second semester, we used to have environmental chemistry subject, and Pandey sir used to teach us. And when I was doing my slides, and he is the one, he was right in front of me. And when I saw who will be there, and I saw Pandey sir, oh, it's gonna be great pleasure to talking about the environment, and your environmental teacher is right in front of you. So
Thank you.
it's my pleasure, sir. And I really respect you and your teachings. The way you have taught us, it's still we are the same. We are carrying with us in here as well. Thank you so much.
Thank you.